Okay, hi everyone. So I'm recording this after our lecture, our Monday lecture. Unfortunately, it seems that I think I messed up with PV Collaborate, the recording thing. I can't find the recording there. I don't know what happened. I'll figure it out so that we don't have this problem next time. But I'm recording this video now, just sort of a quicker version of the lecture that I just gave you guys at 12. And I'll post this on YouTube. So we started with 3 remarks. So now in these remarks, I'm going to assume that, so the first remark is the following. Suppose K is a splitting field over F, so a splitting field of some polynomial. When you say that K is a splitting field over F, by what you mean is that there's some polynomial G with coefficients in F such that K is a splitting field of that over F. And now let F with coefficients in F be irreducible. Then well, the Galois group of K over F would act on the set of roots of F in K. And the claim is that that action is transitive. Then the action of Galois group of K over F on the set of roots of F in K is transitive. So this is exercise, this is related to exercise 73 of Rotman. It's actually exactly exercise 73 part 1 of Rotman, except that in that exercise I told you that you can assume that K is a splitting field of F. Right? I said that, feel free to add that extra hypothesis that K is a splitting field of F, but you don't need that extra hypothesis. If K is a splitting field over F of some polynomial G, and F is some irreducible polynomial with coefficients in F, then the action of the Galois group of K over F on the set of roots of F in K will be transitive. And just to sort of, we did this in more details during the lecture actually, but I'm just gonna give a quicker version of it here, with less details here. So let alpha and beta in K be roots of F. Now, well, we say that when you're saying that the action of the Galois group on the roots of F in K is transitive, what that means is that there's some element of the Galois group, K over F, that sends alpha to beta. Right? That's what we're trying to prove. So now what you do is the following. You start with the following diagram. F identity going to F. Now here you have F alpha, here you have F beta. Now alpha is the root of F, beta is also a root of F. F is irreducible, so by lemma 50, so F is irreducible, alpha and beta roots of F. So you see by lemma 50 of your textbook, there's some isomorphism sigma from F alpha to F beta, from F alpha to F beta, which fixes F, fixing F, extending identity on F, and sending alpha to beta. And mapping alpha to beta. Right, so you get a sigma here, an isomorphism of F alpha and from F alpha to F beta, and then the next step is that now K is up there, and now K is so K is a splitting field over F, right? So say K was a splitting field of field of G over F over F. But now K is also a splitting field of the same polynomial, but over F alpha and over F beta. So K is a splitting field of G over F alpha over F beta. And now, well, G sigma star of G, what's sigma star of G? Well, because G has coefficients in F and sigma acts like identity on F, sigma star of G is just G itself. And now your lemma, sorry, your theorem 51. So now theorem 51 of Rodman, implies that sigma extends to an isomorphism, isomorphism from K to K. So an isomorphism sigma hat of K. So sigma extends to a sigma hat, and that sigma hat, well, extends sigma, so it sends alpha to beta, and, well, again, it extends sigma, so it acts like identity on F, so it's an element of the Galois group of K over F, and sends alpha to beta as desired. So that's the first remark, that if K is the splitting field over F, and little f is any irreducible polynomial with coefficients in F, then the action of the Galois group of K over F on the set of roots of F in K is transient. Now note that here we're not, I mean, this statement here made no assumption or assertion about whether F actually splits over K. Right? I mean, the statement is true even if F doesn't have any roots, and the proof stands. Even if F doesn't have any roots in K, still you're fine. The set of roots of F and K will be empty, and the action on it is transient. Okay, so now the second remark, let me stay aside for like a few seconds, and then erase this board. So I want to keep the first remark, it's a statement on the board. The second remark now is the following. It's related to the comment that I just made. That here we're not saying, the statement here didn't say that, you know, F splits over K. Right? But now the second statement, the second remark is the following proposition. So this is you prove so in problem set 9, the problem set that was just posted, question 1, you prove the following. The following proposition, that let K be a splitting field over F. F be an irreducible polynomial. Okay. Again, here we're not assuming that K is the splitting field of F. No, it's just splitting field of some polynomial, and F is some irreducible polynomial with coefficients in F. Then, or let's write it like this, suppose F has a root in K. Then F actually splits over K. Okay, so if K is a splitting field over F, and if I have some polynomial, some irreducible polynomial, that irreducibility is absolutely crucial. If I have some irreducible polynomial over F, which has a root in K, then it will actually split over K. Okay? So in this statement and in the proof that you're going to give on your homework, both of these assumptions, that K is a splitting field and that your polynomial is irreducible, both of those are absolutely crucial. There's a hint posted for the question as well, and I'll be more than happy to discuss it in office hours this week as well. Okay, so now, combining these two remarks, we get the following. So 3, this was called the remark 3 in the lecture, so let's do the same thing here, is the following. So suppose, again, K over F is a splitting field. K is a splitting field over F. F is irreducible. With the roots alpha in K. Okay, so K is a splitting field, K over F is a splitting field extension, and you've got this irreducible polynomial F, which has a root in K. Okay, so by this proposition, the proposition tells us that the polynomial actually splits over K. So by remarks 2 and 1, okay, so 2 would tell us that F actually splits over K. F splits over K, because it's got one root there. It's irreducible over F, and K is a splitting field. And, okay, so that's by 2. And now, by the transitivity of the action of the Galois group on the set of roots of F, the set of roots of F in K is equal to the following set. It's the set of elements of the form sigma of alpha. Well, sigma is an element of the Galois group of K over F. So this is because, well, every element of the Galois group of K over F permutes the set of roots of F. So each of these sigma of alphas is indeed a root of F. So that portion is fine. The right-hand side is indeed in the left-hand side. For the reverse inclusion, if I give you the reverse inclusion is by the transitivity of the action of the Galois group on the set of roots of F and K, right? So if you give me any roots beta of F in K, we saw that there's an element of the Galois group that sends alpha to beta. So beta is a sigma of alpha for some sigma. So those were the 3 remarks that we discussed first, and then the next thing we did was that we did an example